So 6-1 is all about growth and decay. Now we've already seen multiple types of functions. We started off in Algebra 1 with linear functions, which was just a line. Pretty straightforward. Here's my line. It followed the standard equation y equals mx plus b. And you should also have learned in Algebra 1 or been introduced to the quadratic section, but this is usually focused on more in Algebra 2. But we had our quadratics, which was a parabola, and again, we would have a standard equation, and the standard equation would be y equals ax squared plus bx plus c. So we have two major types of families of functions. So in this section, we're learning about the third major type, and that is going to be exponential. Exponential. Okay. And so this is going to be a picture that either looks like this or like this. One of the two. And it follows the standard form of y equals a times b to the x power. And as we can see, it does follow the name exponent and putting the x in the exponent as opposed to having it anywhere else. So we're going to discuss what a and b represent. If we're just given an equation, a is going to be our y-intercept. But you can use this in real-world situations, especially concerning money. And so if we have a problem like that, typically it's going to represent our starting value, or our initial value. It all means the same thing. B, however, is going to be our rate of change. Just like back in Algebra 1 with our linear functions, m was our rate of change, our slope. And so for the standard form of the exponential function, b is going to represent that. And below, I actually told you that if b is greater than 1, we know that it's going to be growing. And so the picture should look something like this, and it goes upward. If it is decaying, though, that's going to be between 0 and 1. And again, we're going to have our coordinate plane here, and the picture is going to be going downwards. Now remember, we know if it's increasing or decreasing or growing or decaying in this particular case because as I teach in class, you would put a little roller coaster on the left-hand side, and if it's going upwards, that's growing, and the one beneath it, we put a little roller coaster again on the left-hand side, and it goes downward, which is why it's decaying. The other thing I need you guys to know is this word asymptote, sort of like isotope, but asymptote, and the asymptote is an imaginary line, that a graph approaches, but it never crosses. So if you look at the picture, I went ahead and put the asymptote as a pink dotted line. And typically we represent this by equation y equals 0. And it will always be y equals 0 unless we have a translation, which we'll get to eventually. All right, so let's go ahead and graph a couple of these. So example 1.1, A on the left-hand side, it says, first of all, tell whether it is growth or decay, and then graph the equation. So our equation is y equals 2 to the x power. Well, if I were to follow my y equals a times b to the x power, I can see that this is my b value, all right? And I know it's my b because it's my base of the exponent. Therefore, this is my b. So the question is, well, what is my a? Well, just like back in Algebra 1, if you're just given x and no coefficient, it's always an understood 1. And the same thing applies here. We don't have our a value, so it's going to be an understood 1. But remember, a represents our y-intercept. So if I want, I can go ahead and plot the point, the y-intercept on the coordinate plane, and I can even include it in my graph on the right-hand side, or my xy chart. Now here's something I strongly recommend you write down. If your y-intercept, actually I'm not going to write it there. If your y-intercept, I'm going to put it down here because I'm not actually going to do anything down here. If your y-intercept is equal to 1, then you will have a point at 1, b. So if we had a y-intercept at 3, we would have to do something slightly different to figure out how to graph it. But in this particular case, it's going to be y, if y is 1, which is all of these particular cases, then the next point is 1, b. And I already know what 1b is. I already know what b is, and that is 2. So I can put another point at 1, comma, 2. All right, so I have 2 points, but that's not enough to have an exponential function. So there's one or two things you can do. The first thing is you can use a calculator and get your values that way, or you can just plug it in to your formula. It doesn't really matter. I don't have a calculator with me right now, so I'm just going to go ahead and plug it in and get my answers. So if I plug in a 2, because those are easier to do right now, it's going to be 2 to the power of 2, which is equal to 4. If I were to plug in a -1, it'd be 2 to the power of -1. And this is something we learned back in chapter 5 with our exponents. If you have a negative exponent, you just need to bring it downstairs or upstairs if it's already downstairs. It needs to change floors. It's unhappy where it's at. So it's now going to say 1 over 2 to the first power, which is just 1 over 2. And then finally, we have our 2 to the negative second power. Again, we change floors because it's negative, it's unhappy. And now we can say, okay, it's going to be 1 over 2 squared, or 1 over 4. Now, once you start doing this, you can sort of see a pattern that arises. And the pattern is at the center, if you will, of our graph. Our center is going to be our y-intercept. If you notice, if I were to take 1/2, I can actually make it 2 by writing the reciprocal. Because if you think about it, 2 can be written as 2 over 1. So these are actually reciprocals of each other. All right? I can do the same thing right here. 1 over 4 can be written as 4 over 1. And so what's true one way is true the other. And so we can see this pattern arise in this particular case. Another really cool thing is that another reason why I may not need a calculator is because I can actually get my answer by taking my rate of change, my b value, and using it to multiply my y values. So if I had 1/4 and I used my calculator, if I had 1/4 and I multiplied it by 2, it would give me 0.5 or 1/2. If I were to take 1/2 and multiply that by 2, I would end up with 1. If I were to multiply that by 2, I would get 2. Multiply that by 2, you get 2. So we can see that whatever you can multiply all of these numbers by to get to your next one should be the rate of change or the base of your exponent. So if I wanted to, I could keep going. I could say, okay, well, my next number would be 3, and then 4 times 2 is 8. The number after that would be 4, and 8 times 2 is 16, etc., etc., etc. And I could keep going, but I'm not going to. So we can see two of these patterns arising from exponential functions, which is a very nice thing, especially when you don't have a calculator. You can just follow the pattern. So let's go ahead and graph this, and we can be done with it. -2 and 1/4, that's going to be right around here. -1, 0.5 is right there. 2, 4 is going to be at this location, and even though it's not part of it originally, I can, in fact, put 3, 8. 4/16 is too high, so I don't have to worry about that one. And then I just connect my dots, all right? Please remember there is that asymptote, that understood imaginary line that prevents the graph from going lower or going to the other side. All right, so same idea with the next one. And again, we can do this instead of plugging into my equation. I'm just going to follow my pattern. So first things first, I have a understood A or y-intercept of 1. So I can fill all that in. And then I have my base, or my b, is equal to 4. All right, so I can say, all right, this is going to be following 1 comma b, or 1 comma 4. That is 3, my bad. 1 comma 4. Change the color and put that in right here. All right, so then I can use this. I multiplied by 4 to get here, which makes sense because that's my rate of change. I multiplied by 4, so that means I need to multiply by 4 again and to get my other y value, and it will be 16. Then I can use my pattern that I saw earlier. This is my center. I'm going to take this 4 and write the reciprocal over here. So this will be 1 over 4. Same thing with my positive 2. I can use positive 2 to find the y value of -2. It's the reciprocal, or 1 over 16. And so this is going to be, if I were to create my dots, plot my points, if you will, it's going to be something like this. There we go. And again, we have our asymptote, and I'm not always going to state it. I'll probably talk about it again when we get to 6-4, which is all about transformations of exponential and logarithmic functions, which we'll talk about later. All right, so this has all been growth, as we can tell. Again, we can put a little roller coaster right here. It would be going upward. Put a little roller coaster on the left. It would be going upward. So we can see that this is growth. And in addition to that, our B value is greater than 1. If it's greater than 1, we know it's going to be growth. So in part B, our B value is now 1/2. It is less than 1. And so this should be decay. But let's just say we don't know that. We'll just say decay question mark. Like maybe, but it's definitely going to be, but it's fine. First things first, I have an A value of 1. So I'm going to put that here, 0, 1. I also am going to have a ordered pair at 1, B, which is 1/2. So 1, B, 1/2. All right. And then if I wanted to, I can plug in my 2 value here. Let's see, it's going to be 1/2. Okay, and make sure you use parentheses. Raised to the second power. That's the same thing as having 1 squared over 2 squared, which is 1/4. All right. So remember, if this y-intercept is my center, then I can use the reciprocal and fill it in here. So the reciprocal of 1/2 is 2. Reciprocal of 1/4 is 4. All right. So I've used my pattern. I'm ready to plot my points. So it's going to be -1, 2, and -2, 4. If I wanted to, I could find the other point. And it's going to look something like this. All right. So again, we can see we have our exponential decay. Again, we can put our little roller coaster on the left-hand side. This time it's really high up, and we can see it's going down. So we, in fact, have confirmed that this is going to be exponential decay. All right, 2/3. So again, this is the same idea as we've done before, but I just wanted to add a more complicated fraction so that we could see, the pattern again. Our A value, again, is 1. So my y-intercept is 1. My B is going to be 2/3. So I'll fill that in. It's going to be 1, 2/3. I can use this to get my y value here by just doing the reciprocal. That's 3/2. And then I can plug into my equation. Let's say I have 2/3 raised to the second power. That's going to be 2 squared over 3 squared, which is 4/9. And again, you can use a calculator and to get all these values, but I don't have one, which is why I'm doing it this way. And then 4/9 can be used to find the y value of -2, and that's going to be 9/4. So if you use a calculator, you can easily get the decimals, and it might be easier to use whenever you're graphing. But I have 0, 1, 1, 2/3, which is about 0. It's 0.6 repeating, so it's going to be just above that halfway mark. And 2 and 4/9, which is 0.4 repeating, and that's just below the halfway mark. The other 2 points are -1, 3/2. 3/2 is 1.5, basically. And then -2 is 9/4. That's 2.25. So it's going to be something right around there. All right, so this one's quite a bit flatter, if you will. And it makes sense because we have a fraction. So we know based off of our concepts in algebra that it is shrinking. It is compressing, if you will. All right, so we've drawn our pictures and we've filled in our XY chart, and we've noticed 2 patterns. We've noticed that we can get to our next values by multiplying by our B value, our rate of change, and then we can also find our Y values by using its corresponding number and just using the reciprocal. All right, so let's move on to some other items. What if instead of them asking you to multiply and create the graph, what if they gave you the graph and said, we want you to write the equation. So if you have an older version of the notes, this might be a little bit different, but hopefully you have new ones now. In the first 2.1 example, I have a very similar problem from the homework. I have 0, 1, and then I have this other point, 1, 3. Remember, if we have 0, 1, all right, our y-intercept, A, is 1, we are allowed to use this point, 1, B, 1, B. This becomes my b value. So if I am trying to plug into my equation, remember my equation is a times b to the x power. All I need is a and all I need is b, and I found both of them already. So my answer is going to say y equals 1 times 3 to the x power, and I can clean that up a little bit, and I can just say it's going to be y equals 3 to the x power. All right, so again, this is based off of our y-intercept if it is equal to 1. But what if it's not 1? What process would it be then? Well, again, we can look at our picture on the right-hand side, example 2.2. We have a y-intercept at 3. So I know that a is equal to 3. If I were to plug that into my equation, it would be y equals 3 times something raised to the x power. All right, and the question is, well, what is this something? What is this going to be? All right, to figure out what it's going to be, what I strongly recommend is you create your own XY chart. All right, so I have the point 0, 3 already, and I want to find another point that is right next to 0, a whole number specifically. So I have 0, 3. I also have this -1, but I have no idea where it hits here. I don't really know. I could guess, but I could be wrong. However, I do have a point at 1 instead of -1, and it hits right at the intersection. So I know it's going to be an exact number. It's 1, 6. So I do in fact have two points that are right next to each other. And remember how I said that b is your rate of change? It's what you use to multiply to get to the next number. So the question is, what do I multiply the 3 by to get to the 6? And the answer is 2. So I know that my rate of change is going to be 2. So I can clean this up a little bit. Y equals 3 times 2 to the x power. And this is the equation. So it's not necessarily harder, but it does require you to think about it in a slightly different manner, and it's just not as straightforward as example 2.1. All right, so we've dealt with an equation and creating the graph. We've dealt with a graph and creating an equation. What if they don't give you an equation or a graph? That's when we come to example part B. It says a certain bacteria triples every 3 hours. So the word triples right here, this is letting me know that it is my rate of change. And specifically, it would be 3, because tripling would be like multiplying by 3. Just like doubling would be multiplying by 2, or quadrupling would be doubling by, or not doubling, but multiplying by 4. So a certain bacteria triples every 3 hours. This word every is significant. So I'm just going to hold off on this information for a second. If you start with a culture that is 51 particles, all right, that is my starting amount. All right, and as I said before, your starting amount is going to be A. What will your culture count be after 18 hours? So I still have that 18 hours and that 3 hours I got to figure out. But for now, I can create my equation pretty easily. It should be y equals 51 times, actually let me use parentheses, times 3 to the x power. So I have this equation. Now I have to plug in my value or my number for hours to get how many particles I should have after this allotted time. So just a quick note, anytime you have time, typically I would say 99.9% of the time, you're going to plug it in for x. Here's the issue though. This triples after every 3 hours, okay? And I'm waiting 18 hours in total. So really the question is asking, well, how many 3-hour cycles are in 18 hours? And the answer is 6. If you want to think about it as you're dividing 18 by 3 to get 6, then that's another good way to think about it. So I'm going to plug in y equals 51 times 3 to the 6th power. So I'm going to take my calculator, and I'm going to make sure that when I do this, I use parentheses. If you do not use parentheses, Sometimes it causes issues, and I just want to make sure that does not happen to you. So it should be 51 times 3 to the 6th power. This is going to give me y equals 37,179. And since it's a word problem, I am going to include the word particles. Particles. How do you spell particles? Particles. I'm a math teacher, not a spelling teacher. All right. So just pointing that out, just to really make sure we understand it, let's do part B on the right-hand side. It's the same thing again. We are doubling. All right, doubling is when B is equal to 2. Every 2 hours, the word every is significant. If you start the culture at 24, that's going to be my A, 24. How many will you have in 10 hours? 10 hours. Okay, so I can create my equations. Y equals 24, that's my starting amount, times 2. Actually, I want to use parentheses. Times 2 to the x power. X is always my time, but remember it says every 2 hours. So how many 2-hour increments are in 10 hours? It should be 5. Again, think about it as we're dividing 10 by 2, and then equals 5. So it would be y equals 24 times 2 to the 5th power. So plug that into the calculator, and we should get 768 particles. I think I got it this time. Particles. There we go. All right. And that's that. All right. So everything we've been doing has been based off of Algebra 1. So let's get into some more Algebra 2 material. In the previous example, whenever we had the words doubles or triples or anything like that, we already knew what to do, if you will. But in this particular section, it's, well, what if they give you a percent? So let's talk about it. Let's say we had the same problem we had before. We start off with 24 bacteria particles. And instead of doubling, all right, let's say it increases by 5%. So anytime you're given a percent, the first thing you have to do is you have to change it to a decimal. All right, so technically the decimal is after the 5. You always need to go 2 times to the left. And if you have an extra bump, you just need to fill in a placeholder, which is always going to be 0. So 5% turns into 0.05. I'm not one of those teachers who requires you to have that 0 in front, so whatever. So I found my rate, if you will. So I'm going to plug that in, and it's going to be, actually, I am going to include the 0 this time because it's going to be important later. 0.05 raised to the x power. Okay. There is an issue with this problem because I said that the bacteria should increase by 5%, right? But unfortunately, my rate of change is 0.05, which is significantly smaller than 0, or significantly smaller than 1. And so because of that, what I need to do is I need to actually make it bigger than 1 to represent that it is growing. So I'm actually going to add 1. So the formula they use is just by adding 1 or subtracting 1. It does not matter. All right, so this is what it should be. And again, this is only when you are given a percent. Given a percent, all right? So when you're given a percent, you need to use this formula. If they use the word double, triple, quadruple, half, whatever, obviously those are, you just use the numbers. But if you're given a percent, you have to use this formula. So let's practice that. Let's say a car of $11,300. Okay, so that's my starting amount. Depreciates, that means I'm definitely decaying, depreciates at 11%. So if I'm depreciating, I need to use the formula 1 minus my percent, or 0.11. What is its value in 5 years? Remember, if it's time, it should be plugged in for X. Sometimes it's represented by the variable T, all right, because it's time. So I'm going to plug this in. It's going to be 11,300 times 1 minus 0.11 to the X power. Technically, Y equals. If you would like to make it a little bit simplified, 1 minus 0.11 is 0.89 to the x power. Okay, so I'm going to take my calculator, 11,300 times 0.89 raised to the power of 5, because this is for 5 years. And notice how I don't have the word every anymore, so I don't have to worry about dividing my years by anything. So I am taking this and plugging in the 5, 11,300.89, raising it to the 5th power, and I get $6,309. And we're talking about money, so we run around to 2 decimal places, so it'd be 99 cents. So the car is going to be worth $6,000. It's going to be worth about half. All right. Part B, what if it is growing? If we have $1,000, all right, so that's my A value. It grows, that's going to be adding to 1, 2.3%. All right, so remember, 2.3%, we take our decimal, we go over to the left. All right, so my decimal is now here, and any other thing that any other space that we have, we need to fill in with a 0. So that's going to be this. So if I plug into my equation, it should say 1,000 times 1 plus 0.023 raised to the x power. We can simplify that by making 1.023 raised to the x power. And then it says, well, what will the account be worth in 20 years? So we're going to plug in our 20 here. Ignore how terrible that 3 was. It's not my finest moment. Raised to 20 years. And we end up with, something tragically small. $1,575.84. So this one did not grow very much at all. But that's okay. We'll get to what banks actually do in a second. So the next part is very similar to what you're going to have on your homework. We have this word problem. It's a very good word problem. It says the value of a car can be modeled by the equation y equals 25 times, I'm actually going to write it, y equals 25 times 0.85 t to the power of t in the thousands. So basically all they're saying is that this 25, it doesn't represent that the car is $25. It represents that the car is $25,000. All right, they just didn't feel like adding all those zeros. Where t is the number of years since the car was new. So A, tell whether the car is following a growth or decay model. Well, obviously, if we look at our base of the exponent, it's 0.85. Well, that is smaller than 1. So part A, we would say it is decay. All right. Part B, identify the annual percent increase or decrease in the value. Now, here's where a lot of people make a mistake. They look at the 0.85 and they say, oh, it's decreasing by 85%, but that's not actually true. Remember, the equation is 1 minus the rate, which is what we're looking for, and that happened to equal 0.85. So you can either look at this and sort of figure it out, think about like $1 and how much money did you take away to get 85 cents. You can look at it and sort of figure it out. Or if you're like me, you have to do the steps, and there's nothing wrong with that. So I'm going to isolate r by subtracting 1 on both sides. That's going to give me negative r is equal to negative 0.15. All right, I need to get r by itself. It still has that negative with it. So I'm going to divide each number by negative 1. And I get my rate is 0.15 or 15%. All right, so then part C comes. Part C says estimate when the value of the car will be 8,000. Okay, so remember they got lazy with the thousands, so I'm just going to say 8 is equal to 25 times 0.85 raised to the t power. Now, there's 3 ways you can do it. The first way is solving for t, which is actually something that you guys haven't learned yet. I mean, you've learned the process of solving for t, but not in this particular context where the variable is the exponent. But we're going to get to that tomorrow, so don't you worry. We'll get there eventually. The second method is like a plug and chug method. I can plug in to y, 1, 2, 3, until I find when it's about 8,000. However, it could take me 15 tries. What if the answer is 15 years, So that could be used. But the third way is probably the best way, and it would require you using your graphing calculator. So you would go into your y equals portion, all right? And I obviously don't have my calculator, so I'm just going to instruct you how to do it. It should be y equals, and I'm going to plug in my equation, 25 times 0.85 raised to the t power, or since your calculator only does x, it would be raised to the x power. But remember, x and t are basically the same thing. All right, so after this, I could see the picture, but it's actually not going to tell me anything. So I want to see the table. The table is going to tell me a whole lot more information. So I'm going to press second and then graph. All right, that brings me to the table. All right, and so you should end up with an XY chart. Should be very pretty. And you are looking for, remember, X represents your time, and it's your, trying to change the color here. It's your Y value that is going to represent your value of the car. So you're looking for when it equals 8, not 8,000, because we're not including those zeros. So we're looking for when it equals 8. And if you look at it, you should be able to see it when X is equal to 7. So remember, X is your time or your years. So we would say the answer to part C is about 7 years. Okay. Estimate when the value of the car will be 8,000, about 7 years. All right. So I do want to point out one thing. Over in part D, and again, you might have some notes that are slightly rearranged, but over in part D, part A says write the function. That's same old, same old. It's just like part B that we had in this example. Part B says estimate the number of subscribers in 2008. All right, that's basically this work again that we had right here, done for part B. And then part C says estimate the year when subscribers will be 278 million. Okay. Again, they are not putting in all the zeros. So for this one, the process is the same as before. You have your XY chart. All right. We have our values for X, values for Y. Eventually, you're going to have one that's 278. All right. And I think it's 3 years or something. I don't really remember, but it's something like that. So the important thing about this problem is that a lot of people make the mistake of saying that the answer is t equals 3 years. But the question is not asking how many years. It's asking in what year. Estimate the year that you will have subscribers be this. And they want you to use the information at the very beginning. They say, okay, well, we started this study in 2006. So if it takes 3 years to have the subscribers we're looking for, we need to add that to the year that we started the study. And so really, the answer is going to be 2009. And I just want to point that out because it's a very common thing that the SAT and the ACT do to make sure that you're actually paying attention to the question. They're not asking you how many years, they're asking you in what year will this happen. All right, the last thing I want to point out in this particular example is letter D on the left-hand side. It says the amount of Y in the radioactive isotope iodine-123 remaining after T hours is given by the equation, and they give you this lovely, complicated-looking equation where A is the initial amount. What percent of iodine-123 decays each hour? So this one throws people off because typically we're used to part A, part B, part C. Part A, part B, part C. Part A, where is it? Part A, part B, part C. This one doesn't have part A, part B, or part C. You don't have to worry about that. Really, all we're asking in this particular problem is only about part B, which is what percent decays each hour. So if I have the decay model, that's 1 minus R, is equal to what I was given, which is 0.5. All right, I'm going to solve for R. Subtract 1 on both sides. I end up with negative R equals negative 0.5. Divide by that negative 1, and I get R is equal to 0.5 or 50%. All right, so even though it seems like it's a little bit more complicated, especially since they randomly throw the initial value as A, like that's just extraneous information. They're trying to throw you off. All right, what you care about is what is the percent of decay each hour, and we found it. All right, so the final thing that exponential functions are really, really important for is compound interest. So remember how we had that bank account and we like deposited $1,000 and then we waited 20 years and we only gained $500. That is a terrible, terrible bank account. Thankfully, most banks follow a compound interest model, which is great because as we can see, it'll be better. And obviously, you're just going to take my word for it now. And again, this was taught back in Algebra 1. So let's just make sure that we remember some of these variables. P is going to be your principal, or aka your starting amount. Oh my goodness, it's like the same thing as what we had at the very beginning. In fact, it's the same formula. It's y equals a times b to the power of x. They just changed it slightly to compensate for money. All right, so we have that principal. The next one is r, which is our rate. This is always going to be represented by percent. The next one is our n, which is actually in two locations, the denominator and our exponent. Okay, and this is going to be the number of times that the interest is taken per year. So if they said yearly, it'd be 1, or semi-annually would be 2, quarterly would be 4, monthly would be 12, etc., etc., etc. And then the last one that we have is our t, which is sort of hidden, but t is obviously going to represent time, and time is always in years. It's always in years. Okay, so really this is just a plug and chug type of formula. I'm just going to plug it in. So it's going to say, all right, you deposited $9,000, that is my principal, in an account that pays 1.46%. All right, I'm going to go ahead and turn that into a decimal. All right, I have 1.46. I need to move my decimal 1, 2. So my decimal is now here, which means I have a placeholder of 0 right there. All right, find the balance after 3 years. 3 years is going to be my t. And then it says compounded quarterly. Remember, quarterly means that it happens 4 times a year. So then I just plug it into my equation, or my formula. 9,000 times 1 plus 0.0146 over 4 times to the power of 4 times 3. All right, please make sure that you multiply that exponent. I have noticed a lot of kids forget it, and it does cause issues. So we're going to plug this whole thing into our calculator and make sure that we raise it to the power of 4 times 3. And we should end up with the answer of $9,402.21. And this is our answer. All right, well, I hope that was helpful. And if you have any questions, make sure you reach out.